Hey y'all, welcome to BCA Tables with moles. So this is going to just be an introduction on how to use BCA tables with solving for chemical quantities. So let's go ahead and jump into question number one. Nitrogen gas and hydrogen gas react to form ammonia. How many moles of hydrogen are needed to completely react with 3 moles of nitrogen gas? All right, so whenever we have these type of problems, we need a balanced equation. So let's go ahead and write out our equation for this. We got nitrogen gas reacting with hydrogen gas, and both of these are diatomic molecules. So we're going to have a 2 there, and they are forming ammonia. All right, if you'd like to pause the video and try to balance this equation yourself, you can go ahead. But let's go and get these coefficients out here. Let's go and change the color up as well. So we'll go with green. We got 1, 3, 2. All right, cool. So we got our balanced equation here. And a balanced equation serves as our recipe in how these reactants and products react with each other and form too. So all these things are specific ratios that, just like how if you were cooking something and you needed like certain ingredients to make so much product, this is the same thing. So our BCA table is just kind of listed out there, or listed under there underneath our equation. The B is just going to stand for before. So before the reaction occurs, we're going to go ahead and just fill this row up with what we know. Looks like we have 3 moles of nitrogen, and we don't know how many moles of hydrogen we have, right? We're trying to look for how much is going to react over here, and it doesn't tell us how much product we have. But if this is before the reaction, we are going to have 0. So anytime the reaction happens, then we start making our products. But before that, products are always going to be starting off at 0. Start at 0. Right, we need the molecules to react with each other to make products. All right, so we got our before row done. We're going to go ahead and jump over to our change. And let's go ahead and change up colors. So with the change, again, just like how there are specific ingredients to bake a cake or something like that, there are going to be specific ingredients that go into here, and those are based on the coefficients. So the change is going to be based on the coefficients for here. So we're just going to use a random variable. We tend to use x, because of mathematics and all that. So we're going to go ahead and use change. We're going to say that this is going to go down for our reactants, because the reactants, they get used up as the reaction occurs. So we're going to be going down. And for our change, this is our coefficient of 1. We're going to go down 1x. Hydrogen gas is also going to get used up, right? So as nitrogen and hydrogen molecules collide, they're starting to form some NH3 or ammonia. So we're using up some hydrogen gas. And how much hydrogen gas, or what's the coefficient here that we're going to go down by? We're going to go down by 3x. So we're going to go down by 3x. So our change row is based on those coefficients. All right, now we're getting to our products. So our products, instead of going down for our reactants, they're getting used up. What's going to happen to our products? They're going to go up, right? We're going to be making that stuff. So instead of going down, we're going to be going up for our products. We're going to start producing stuff. And then what x do you think we're going to put there? That's right. We're going to put up a 2x. So we're going to be going up 2x. So here's our specific ratio. This is all coming from the coefficients of our reaction. That's an IE. All right. And so here's our change. All right. Last part is going to be our after. So let's change back to green. So green, we are putting our after. And so after the reaction occurs, we aren't going to have any more nitrogen gas, because we're looking for this stuff to completely react, which means we want all our reactants to be used up. So we're going to be left with none of that. We're going to be left with none of hydrogen, right? If we want just the specific ratio of them to completely react with each other. And then ammonia, we're not sure how much we're going to produce yet, so we'll leave that blank. But we know that's going up 2x. All right, looking at our columns here, do we have a specific column that is already all filled up? Yeah, we do, right? So looking at it, we are going to look first just to find out what X might represent. So over here, we got our nitrogen row or column, my bad, already filled up for us. So just looking at this, if we're starting off with 3, it's going down by X and ending up at 0. What is X going to be? It's going to be 3, right? So if I got 3 minus X equals 0, my X is going to represent 3. Right, so if I just isolate my variable, add X to the other side, X equals 3. So our X is going to equal 3. So now we can kind of use that to go back and try to figure out what our question was asking. So our question was asking how many moles of hydrogen are needed to react. So we were looking for this right here. We want to know how many moles of hydrogen are going to completely react with nitrogen gas. So we know that X is 3. So we can come back over to this one now. What color have we used? Back. So we can come right over here and sub that in to find out what our question mark is. For our question mark, let's go and just put this as the label hydrogen, right? So we want to find out our initial amount of hydrogen. So I'm going to just write this equation down here. Hydrogen is going down by 3x to get to 0. We know what X is now, right? So we know X is 3, so we're just going to sub in 3 for that. 2 minus 3 times 3 equals 0. So we got H2 minus 9 equals 0. So H2 is going to equal 9 moles, right? So, yeah, so that's going to make sense, right? So we just subbed in 3. We got H2 minus 9, add 9 to the other side. So there are going to be 9 moles of hydrogen gas that needs to completely react with 3 moles of nitrogen gas. So our final answer for this one is going to be 9 moles. And we can even look back at the equation, right? For every 1 mole of nitrogen needs 3. So every 3 moles of nitrogen is going to need 3 times that. It's going to need 9. So sometimes the numbers get a little trickier. This is just whole numbers, so it's a little bit easier to see initially. But once you have this BCA table set up, you can use it to solve for other equations too. Or not other equations, but other quantities too. Like if I asked you, you already have this table set up, how many moles of ammonia would you produce? What do you think that would be? So if 3 moles of nitrogen gas completely reacts with hydrogen, how many moles of ammonia do you think we'd produce? Think about it. All right, let's take a look. So did you say 6, right? So looking over here, how many moles of ammonia we're going to produce? So here's our after, right? So we've used up all our reactants. Ammonia is going from 0 up to X. We know that X is 3. So we got 2X. So all we're doing is we're subbing in 3 for it. So we should get 6 moles of ammonia. So we should get 6 moles of ammonia produced from this reaction. So really it just depends on what they're asking you. But once you've set up a BCA table, you can kind of just use that to figure out whatever quantity you need. All right. Let's take a look at one where I want you guys to try it. So over here, we have the second question, Q2, question number 2. Not sure why I'm saying that so much. So question 2 is methane combusts to form carbon dioxide and water vapor. If 4 moles of carbon dioxide are formed, how many moles of methane were burned? So pause the video, try to write out what you think the equation would be. All right, so we got methane. So methane is CH4. And if we have a combustion reaction, what does methane have to react with in the air? Oxygen, right? So it reacts with oxygen, and then we're saying it's forming carbon dioxide and water. All right, so we have our equation there. So again, go ahead, you can pause the video to try to balance it out. And then our coefficient should be 1, 2, 1, 2. We can toss those ones there, but we don't have to put the ones, right? All right. So from here, go ahead and just fill in the table as best you can, and then we'll check in. So pause the video. All right. So hopefully you tried the equation. Before our reaction occurs, we have some amount of reactants. We're not sure what. We have 0 products. We don't have any of that, right? And then our change, we're going down 1x, going down 2x, going up 1x, going up 2x. And our reactants, we're using those up. So after methane gets used up, we're going to be at 0. Oxygen, there's going to be, yeah, we can assume there's going to be 0, but oxygen's in the air. So this is what's something called an excess reagent. I'm going to put XS. So we're going to have a bunch of oxygen, but that's not what we're looking at anyway. We're looking at methane. So we're trying to figure out this. Carbon dioxide. Afterwards, we got it right here, right? We got 4 moles of CO2 formed. And it doesn't tell us anything about water. So from here, we should see that X equals 4. And we know that methane's going down by X to 0. And if we have X, that's 4, right? So we got our CH4 minus X equals 0. Let's go and sub in 4 for X there. CX, CH4 equals 4. So we should end up with 4 moles of CH4. And again, we have this thing set up. So if we wanted to find out other things, we could figure out how much water is produced. So from this reaction, if we had 4 moles of CH4 go down, how much water do you think would be produced? It'd be 8, right? So if 4 moles of carbon dioxide gets produced, 8 moles of water is going to get produced because that's going up by 2x, while CO2 went up by 1x. All right, so this is just an intro to it. When it's not whole numbers, I mean, the math comes a little more important, but otherwise it's not too bad. It's just based on the coefficients of your balanced reaction.